Dr. M.P. Jayaraman is an assistant professor in mathematics in L.N. Government College, Poneri. He has specialized on geometric function theory. With 14 years of teaching experience, he has handled topics on probability and queuing theory, discrete mathematics, random process, and engineering mathematics. Being a recognized supervisor for guiding PhD and MS students of Anna University, he is the reviewer of the journal Computer Mathematics and Applications. He has also written books on discrete mathematics and has also published papers in 28 international publications, in 4 national publications, and has presented papers in 2 international and in 2 national conferences.
Welcome you all for UGC lecture series in mathematics. In this session, our aim is to solve a constraint nonlinear programming problem using graphical method. The idea behind graphical method is we plot the constraint equation in a graph and try to obtain the feasible region for the given nonlinear programming problem. Then we look into the optimal solution from this feasible region. So, by plotting the constraints in a graph, we obtain the feasible region. From this feasible region, we try to find out the optimum solutions. We have seen that in a linear programming problem, the optimum solution obtained in the extreme points. That means, in a linear programming problem, the optimal solution to the LPP is usually found at one of the corner points of the convex region generated by the objective function of the problem. So, in a linear programming problem, the optimum solution obtained only at the extreme point, whereas in a nonlinear programming problem, such condition is not necessary. What I mean is, we can obtain the optimum solution even in the interior point also. So, for a nonlinear programming problem, the optimal solution is not necessarily found at the corner or edge of a nonlinear programming problem. Therefore, for a nonlinear programming problem, the optimum solution obtained either at the interior point or at the corner points. In the graphical method, the first step is we should find out the feasible region for the given nonlinear programming problem. By plotting the constraint equation in a graph, first we have to find out the feasible region. Once we get the feasible region, next we have to find out the optimal point in that feasible region, which we call as convex region. So, the idea in the graphical method is try to find out the feasible region first, then find out the optimum solution in that feasible region. Now, consider the problem. Solve graphically the following nonlinear programming problem, which maximize z equal to 8x1 minus x1 squared plus 8x2 minus x2 squared. Subject to the constraints x1 plus x2 less than or equal to 12 and x1 minus x2 greater than or equal to 4, where x1 and x2 greater than or equal to 0. Verify the above by Hundaker condition, which holds for maxima we obtain. So, we have to solve this given nonlinear programming problem using graphical methods. This nonlinear programming problem involving 2 decision variable x1 and x2 and 2 inequality constraints. Now, the non-negative restriction x1 is greater than 0 and x2 is also greater than or equal to 0. From these 2 conditions, it is clear that in the graph we will consider only the first quadrant. Our concern is only on the first quadrant. Since both x1 and x2 is greater than or equal to 0, this condition satisfied in the graph only in the first quadrant. So, in the graph our concern is only on the first quadrant. For the given problem, the constraint is x1 plus x2 less than or equal to 12 and x1 minus x2 greater than or equal to 4. Now, we will try to draw this constraint in the graph by temporarily ignoring the inequality sign. The first constraint is x1 plus x2 less than or equal to 12. Now, by temporarily ignoring this inequality sign, instead of x1 minus x1 plus x2 less than or equal to 12, we will consider x1 plus x2 equal to 12. By temporarily ignoring the inequality sign, the first constraint becomes x1 plus x2 equal to 12. Now, in this constraint, by taking x1 equal to 0, we will get our x2 value as 12. Therefore, the first coordinate is 0, 12. Then, by putting x2 equal to 0 in this equation, we will get x1 value equal to 12. Therefore, the corresponding coordinate is 12, 0. So, in the first constraint, by temporarily ignore the inequality signs, the first constraint becomes x1 plus x2 equal to 0. By taking arbitrarily x1 equal to 0, we will get the coordinate as 0, 12, and by taking x2 equal to 0, we get the coordinate as 12, 0. The equation x1 plus x2 equal to 12 is obtained by joining the point 12, 0 and 0, 12. Now, we will consider the second constraints x1 minus x2 greater than or equal to 4. Here also, by temporarily ignoring the inequality signs, we will write the constraint, second constraint as x1 minus x2 equal to 4. Now, by taking x1 equal to 0, we will get our x2 value as minus 4. So, the corresponding coordinates are 0, minus 4. Now, by taking x2 equal to 0, we will get our x1 value as 4. Corresponding coordinates are 4, 0. Therefore, the curve x1 minus x2 equal to 4 is drawn in the graph by joining the coordinates 4, 0 and 0, minus 4. Now, we will try to draw that curve in the graph. Consider a graph. This is x1 axis and this is x2 axis. I will consider the scale as 1 unit as 2 centimeter. Therefore, we have 2, 4, 6, 8, 10, 12, and in x2 coordinates I will take the same scale. So, 2, 4, 6, 8, 10, and this point is 12. So, the first curve x1 plus x2 equal to 12 is obtained by joining the coordinates 12, 0 and 0, 12. So, we will join these two points by a straight line. So, this curve is x1 plus x2 equal to 12. Now, by joining the points 4, 0, this is minus 2 and minus 4, and by joining the points 4, 0 and 0, minus 4, we have this equation. This equation is nothing but x1 minus x2 equal to 4. So, from the two constraints, by temporarily ignoring the inequality signs, by joining the curve point 12, 0 and 0, 12, we will get the curve x1 plus x2 equal to 12. By joining the coordinates 4, 0 and 0, minus 4, we draw the curve x1 minus x2 equal to 4. Now, the first constraint is x1 plus x2 less than or equal to 12. Therefore, the corresponding area for x1 plus x2 less than or equal to 12 is towards the origin. Therefore, the area of x1 plus x2 less than or equal to 12 means below this line, below the curve x1 plus x2 less than or equal to 12. Since both x1 and x2 greater than or equal to 0, our concern is only in the first quadrant. Now, consider the second constraint. Second constraint is x1 minus x2 greater than or equal to 4. So, the corresponding area is away from the origin. Therefore, the corresponding area for x1 minus x2 greater than or equal to 4 is this area. Now, the area common to both, that is the area in between x1 plus x2 less than or equal to 12 and x1 minus x2 greater than or equal to 4 is the area of this one. This is the common area. So, the area A and B and C. This area is the common area which satisfies both the constraint. This common area A, B and C is called feasible region. So, a feasible region is the area which satisfies the given constraints. So, by plotting the constraint curve in the graph, we will get the feasible region as A, B, C. Our feasible region is this region A, B, C. This is our feasible region. Now, our optimum solution to the given nonlinear programming problem occurs somewhere in this feasible region, this convex region A, B, C. The optimum solution to the given nonlinear programming problem occur somewhere in this convex region A, B, C. However, the desired point is that which side of this convex region is tangent to the circle. So, our optimum solution occurs in this convex region only, but our concern is which side of this convex region is tangent to the given circle z equal to the objective functions. So, that things we are going to calculate now. So, we are interested in finding which side of this convex region is tangent to the circle. For that, consider the circle given by z equal to 8x1 minus x1 squared plus 8x2 minus x2 squared. Now, the tangent to the circle is obtained by differentiating this equation with respect to x1. So, by differentiating this equation by x1, we have 8 minus 2x1 plus 8 dx2 by dx1 minus 2x2 into dx2 by dx1 equal to 0. So, by differentiating this equation with respect to x1, we have 8 minus 2x1 plus 8 dx2 by dx1 minus 2x2 into dx2 by dx1. Now, we try to simplify this equation. Dx2 by dx1 of 8 minus 2x2 equal to 2x1 minus 8. So, from this equation we have dx2 by dx1 equal to 2x1 minus 8 by 8 minus 2x2. We take it as equation 1. Now, the gradient of the line x1 plus x2 equal to 12 is 1 plus dx2 by dx1 equal to 0. From this, we will get dx2 by dx1 equal to minus 1. We will take it as equation 2. So, in order to obtain tangent to the given circle, first we differentiate the given circle with respect to x1. We will get the equation as dx2 by dx1 equal to minus 2x1 minus 8 by 8 minus 2x2. Then the gradient of the line x1 plus x2 equal to 12 is dx2 by dx1 equal to minus 1. Let us have a break. Welcome back. Before break, we discussed about how to solve a given nonlinear programming problem using graphical method. Now, in this problem, by making use of equation 2 in 1, we have the following. The gradient of tangent to the circle dx2 by dx1 equal to 2x1 minus 8 by 8 minus 2x2. We name this as equation 1, and the gradient of the straight line x1 plus x2 equal to 12 is dx2 by dx1 equal to minus 1. Now, using 2 in 1, equation 1 becomes 2x1 minus 8 by 8 minus 2x2 equal to minus 1. From this 2x1 minus 8 equal to 2x2 minus 8. Now, from this equation we have, by cancelling this minus and minus 8, we have 2x1 equal to 2x2, which gives us x1 equal to x2. So, by making use of equation 2 in 1, we will have the value of x1 equal to x2. Now, with this x1 equal to x2, from this equation x1 plus x2 equal to 12, we have our x1 and x2 value as 6 each. Since x1 equal to x2 and we have the equation x1 plus x2 equal to 12, the solution for this equation is x1 equal to 6 and x2 equal to 6. This means that the tangent of the circle to the equation x1 plus x2 equal to 12 is at the point 6 comma 6. So, the tangent of the circle to the line, this is our line x1 plus x2 equal to 12. So, the tangent of the circle to the line x1 plus x2 equal to 12 is at the point 6 comma 6. But this point 6 comma 6 is not satisfied. This constrains x1 minus x2 greater than or equal to 4. x1 equal to 6, x2 equal to 6, then we will get 0 greater than or equal to 4, which is not possible. So, with this value of x1 equal to 6, x2 equal to 6, the second constraint is not satisfied. Therefore, the solution x1 equal to 6 and x2 equal to 6 cannot be the optimum solution to the given nonlinear programming problem. Now, we go for the other case. Now, we will consider the line x1 minus x2 equal to 4. Now, we will try to find the gradient of this line, which we have 1 minus dx2 by dx1 equal to 0. From this, we have dx2 by dx1 equal to 1. We name it as equation 3. Now, we know the gradient to the tangent of the circle is dx2 by dx1 is 2x1 minus 8 by 8 minus 2x2. Now, we make use of equation 3 in this equation. We have 2x1 minus 8 by 8 minus 2x2 equal to 1, which will be written as 2x1 minus 8 equal to 8 minus 2x2. So, by simplifying this equation, we have 2x1 plus 2x2 equal to 16, which will be written as x1 plus x2 equal to 8. So, making use of equation 3 in equation 1, we have x1 plus x2 equal to 8. Already we have a line x1 minus x2 equal to 4. Now, we try to solve these two equations, we will get 2x1 equal to 12, which gives us x1 equal to 6. Since x1 equal to 6, from this equation our x2 equal to 8 minus 6, which is 2. So, as far as the line x1 minus x2 equal to 4 concerned, we have our x1 value is 6 and x2 value equal to 2. What it means? This means the tangent of the circle to the line x1 minus x2 equal to 4 is at the point 6 comma 2. So, the tangent of the circle to the line, this is our line x1 minus x2 equal to 4. So, the tangent of this circle to the line x1 minus x2 equal to 4 is at the point 6 comma 2. Now, x1 equal to 6 and x2 equal to 2 satisfies both the given constraint. The first constraint is x1 plus x2 less than or equal to 12. So, 6 plus 2, 8 less than or equal to 12. Therefore, first constraint satisfied for this value. Now, the second constraint is x 1 minus x 2 greater than or equal to 4. So, 6 minus 2, 4 greater than or equal to 4. So, with this value of x 1 equal to 6 and x 2 equal to 2, both the constraints are satisfied. Moreover, the point 6 comma 2 lies in this feasible region A, B, C. Since the point 62 lies in the feasible region A, B, C, moreover, this value satisfies both the constraints. The optimal solution to the given problem is x 1 equal to 6 and x 2 equal to 2. So, with this value of x 1 equal to 6 and x 2 equal to 2, the objective function for the given problem is maximum z equal to 24. So, the idea is first we will find out the feasible region from the given constraints, then we look into the optimal solution in this feasible region. Our concern in this graphical method is at which side of the convex region is tangent to the given circle. Now, as far as this problem concerned, we have two set of solution. The first set of solution is x 1 equal to 6 and x 2 equal to 6, but this solutions does not satisfy the given constraints. Therefore, we have to omit these solutions. The second set of solution is x 1 equal to 6, x 2 equal to 2. This solution satisfies both the constraints. Moreover, these solutions lies in the feasible region. Therefore, optimal solution to the given problem is x 1 equal to 6, x 2 equal to 2 and maximum z equal to 24. Now, we can verify Hundaker condition for the given nonlinear programming problem. For the given nonlinear programming problem, we will got the solution as x 1 equal to 6 and x 2 equal to 2. Now, from the given f h 1, h 2, we first will find out the Hundaker condition, then by substituting these 2 points 6 and 2 in this Hundaker condition, we can easily verify the Hundaker conditions are satisfied or not. Let me recap of the points. In a graphical method, our first idea is to find out the feasible region. The feasible region can be calculated with the help of given set of constraints. By plotting the given constraints in the graph, we can obtain the feasible region. Once we obtain the feasible region, the next idea is find out the optimum solution in the feasible region. In the nonlinear programming problem, the optimum solution can be occurs either in the corner points or in the interior of the feasible region. The problem is solve graphically, minimize z f of x equal to x 1 plus 1 the whole square plus x 2 minus 2 the whole square, subject to the constraints x 1 less than or equal to 2, x 2 less than or equal to 1. Now, by plotting these two constraints in the graph, we can find the feasible region first. Once we find out the feasible region in the graph, next we can find the optimal solution in the feasible region. Now, consider the first constraint x 1 less than or equal to 2 and the second constraint x 2 less than or equal to 1. Now, by temporarily ignoring the inequality sign, the first constraint become x 1 equal to 2 and the second constraint become x 2 equal to 1. Now, we try to plot these constraints in the graph. It is x 1 axis and x 2 axis. Now, the first equation is x 1 equal to 2, which is a line parallel to y axis, that is x 2 axis. We take this as unit 1 and this as 2. Now, x 1 equal to 2 is the line parallel to y axis. Then x 2 equal to 1 is a line parallel to x axis, x 1 axis. If we take this as 1 and this is the curve. So, this is the curve x 1 equal to 2 and this is a curve x 2 equal to 1. Now, since x 1 less than or equal to 2, our region is towards the origin. So, x 1 less than or equal to 2 means towards the origin. In this problem also, x 1 greater than or equal to 0 and x 2 greater than or equal to 0, our concern is only in the first quadrant. Now, x 1 less than or equal to 2 means the area towards the origin, we have this one. Now, x2 less than or equal to 1 means the area towards the origin is this one. Now, the common area between x1 less than or equal to and x2 less than or equal to 1 is the area A, B, C and D. So, this is the common area which satisfies both the constraints. So, this is our feasible region. Now, try to find out the optimum solution in this feasible region A, B, C, D by making use of the method earlier we discussed. Thank you.